Welcome to Sober Math. Look at this tiny square grid and this one random square. It fits nowhere on the grid. What else is new? Actually, this square is the average of all the squares on the grid. How? We draw all possible squares, identify their areas, add those up, and divide by the number of squares possible. Here we get an area of 5/3. Easy. It takes longer for bigger grids, but for large grids, believe it or not, this non-fitting average square has a predictable area, and its area is close to, wait for it, 13.33% of the area of the grid, no matter how big the grid is. And the larger the grid is, the closer the average square area is to 13.33%. Math is full of little surprises. But how can I possibly know this? Because the average area is found by this little formula. And so that is what we will derive today. In this video, watch me finally lose my mind and go down the algebra rabbit hole. The point of this video is to make a huge mess and show you how it simplifies incredibly at the end. There will be a flurry of detail ahead, but it's no big deal. I'm using a color scheme to guide the visualization, so you can check my work as we go. It will look like a walkthrough game of pattern matching. As usual, I'll speed through or skip the boring details, but take my time on key concepts. This video follows from part 1 of a series, so I recommend watching that first. Definitely don't worry if you don't get all the details. If nothing else, put it on mute and it will look like a trippy blizzard of rainbow-colored equations. So here we go. Recall the discussion from part 1 with the bilateral grid, where every fitting square is given by parameters L and R. What is the area of this square? Simple. See it? This triangle is a right triangle, and this square is literally off the hypotenuse. So its area is given by Pythagoras. This area is L squared plus R squared. And if L is 12 and R is 16, the hypotenuse is 20. And the area is 400, for example. And all the other squares in its family with the same tilt have the same area, and there are k squared of them. Where here k is 5, and k squared is 25. So the total area of all the squares is a variation of that found in part 1, where the summand is k squared, but now weighted by a common area L squared plus R squared. To start, in the numerator, the summand has to be in terms of L and R, because those are the indices of summation, and k is just n minus L minus R. But if I plug that in, before long, this will blow up out of control. So to make life easy, I'll introduce the parameter x, which equals n minus L. Notice that k is written in two terms, R and not R, because we need to solve the inner sum, which is a sum over R. And now substitute x minus R for k. To solve the inner sum, we want a polynomial in R. So on the side, we distribute. And again. Now we have our polynomial. We plug this into the sum and break up the sum into 5 sums and commute out all the coefficients. To make life easy, I've color-coded everything and labeled these 1 through 5 in Roman numerals, which we move to the side. Already a big mess, but there's hope. We can solve for these one at a time. It turns out that 1 and 2 cancel, so let's get rid of them. We add 1 and 2. The sum over r to the 0 from 1 to u is u, and the sum over r from 1 to u is the youth triangular number, which is written out like this. Plug these in and this cancels, and that cancels, and that cancels, and then boom. Aren't you glad we went with x? And no, it wasn't obvious that 1 and 2 would do this, and this shortcut was found in hindsight. To solve for part 3, we need the square pyramidal numbers by plugging in x minus 1 for u. It's a multi-step process. We solve everything as a polynomial in x, we isolate this factor, and convert it into a little polynomial in x, and distribute this other one to get the 5th polynomial in x. And now the real fun begins, because we need x back in terms of n minus L in order to eventually do the inner sum. So identify all the powers of x equals n minus L. Here are the binomial expansions. And yes, we are going to plug these in for the polynomial 3. Yep, it's getting pretty messy. But nothing mysterious. In fact, here's the rainbow color code. And you can compare like with like. In this next step, we distribute each of the terms. And there's no simple visual way to convince you that these are correct except to ask you to check them. But you could skip all that if you trust me. So assuming that step was correct, we regroup everything to get this polynomial in L and to confirm rainbow to the rescue. So red, orange, green, blue, violet, and brown. Notice I skip yellow, which doesn't contrast against the white background. Now to combine like terms for the coefficients of L squared. Then L cubed, and the rest. I prefer to distribute the factor of 1/6 and reduce fractions. So now 3 is done, and we put it aside for now, until the other two are done. So number 4 is a power sum in R cubed, which is the squares of the triangulars. And for our upper limit of x minus 1, we get this expression. So we cancel and combine powers of x. We can already see that the lowest power when we distribute will be x cubed. I prefer to reverse the order of x minus 1, and then FOIL that square, and then distribute. Again, we've gone as far as we can go with the x, so we plug back in those binomial expansions in terms of L. This time we are spared the powers of 1 and 2, so just the 3 colors. And you can compare like with like. And I distribute the factor of 2 and rearrange terms in powers of L and factor those powers giving their coefficients. So now compare the 0th coefficient and then the first, the third, and the rest. And we distribute this factor of 1/2. And now 4 is done. And now to do last but not least, number 5. The sum from 1 to u of r to the 4th is this expression. Remarkably, we get a very similar expression when we plug in x minus 1 for u. Here are the binomial expansions of relevant powers of x minus 1, which we plug in, and you can compare like with like. Distribute term-wise factors. And regroup terms in like powers of x. And factor those powers. And you can compare like with like. To confirm that we have a polynomial in x. And all these algebraic sums add to 0. And then is just like the power sum over r to the 4th. Would I lie? And again, we've gone as far as we can go with the x abbreviation. And so we have to plug the definition n minus L back in for it. Plug in the binomial expansions over powers of n minus L and compare like with like. Distribute the term-wise factors. You still with me? Amazing. Now we have all surviving inner sum blocks as polynomials in L. We want the inner sum to be a single polynomial in L. So we want to identify coefficients. Starting with C0, we identify these terms and regroup in powers of n this time. These two terms go to 0, and we are left with this small coefficient. C1 is this, and I will now save you time and get to the point and just tell you the coefficients, which are these. And we can finally erase all those very long expressions for 3, 4, and 5. You can always check them for yourself. Either way, you can tell that a lot has to have canceled to arrive at these trim coefficients in L. Now that you have seen this tedious process, I will speed through the power sums. And now to complete this outer sum. Start by multiplying C0 with the power sum over L to the 0. Distribute those factors and put it aside. And then we do the same with C1 and the power sum over L to the 1, which is the n minus 2th triangular number. And plug in the expression. Write it as a polynomial, and then plug back in and distribute again. And put this new polynomial aside. And then repeat for C2. And then I speed through the rest. And then sum over all that gives the outer sum. That is the whole numerator. And we confirm by a little help from our color spectrum. And now, believe it or not, these 4 terms go to 0. And the rest simplifies dramatically. I guess they would have to at this point to provide the formula I claimed. And n squared factors out. Find lowest common denominators to combine like terms. And the expression in brackets factors. So to wrap up, we finally use our formula for the average square area. We divide out the newfound numerator by the denominator that was found in part 1. Explicitly, it is this. We combine and make our final cancellations. And we finally get our exquisite result. 2n squared plus 7 all over 15. What a journey, man! All that work to get one dinky, cute little formula. It makes one think that somehow there must be a shortcut through all this. Maybe through the Bernoulli numbers. Notice when n is larger, the 2n squared overwhelms that 7, and we can ignore the 7. And the average area is 2n squared by 15. If the area of the grid is n squared, then for large grids, the fractional ratio is 2 by 15, which is exactly 13 1/3%. I hope you were impressed by this roller coaster of complication and sudden cancellation. To be honest, I almost always start with a formula first to know what kind of answer to expect. I tried and failed after a couple of tries, so lots of crossed out pages, but eventually I found the correct derivation. So with more practice, you can get better and better at checking your work, and the beauty is that the math itself gives you red flags that tell you how to check it.